This video presents a system that models hand musculoskeletal architecture for the simulation, analysis, and exploration of hand motion. 3 hand models are shown from left to right, capturing the hand in forward simulation, inverse simulation, and showing targeted motion data. The muscles are arranged into 6 groups, according to their anatomic position and depth. The arrows control individual groups. The controllers are used to spread muscles and provide access to various visualization attributes, such as visibility. Muscles are also grouped as antagonistic pairs based on muscle function. Muscles are parameterized to various rest and contracted lengths, with corresponding changes in muscle shape by the length attribute. Transparency values change linearly with contraction, allowing a less obscured view of contracting muscle. All attributes of the muscles are annotated and can be changed in place by selecting the muscle. Peeling back muscle while maintaining tendon connectivity for context is particularly useful for clinically understanding compact hand anatomy. We now simulate flexing the index finger by setting contraction values for the responsible muscle groups. Note the sympathetic motion generated between the fingers on playback. Inverse simulation computes muscle contraction values over time that result in hand motion to match a given target motion. A nonlinear optimization computes contraction values that minimize error between the target and resulting motion. A ghosted hand shows the error in the resulting inverse simulation. Multiple solutions of contraction values over time can result in the same observed motion. Conversely, some synthesized hand motions have no solution and cannot be satisfied with a given musculature. To explore this complex solution space, a clinician can manually change various muscle weights. Here we enable only a small superset of the muscles used in flexing the finger and solve again, resulting in a more accurate match to the observed motion. We also use various clinically motivated heuristics for RSI diagnosis to explore the inverse solution space. Here we simulate muscle fatigue by disabling a set of the most actively contracting muscles in the best fit inverse solution. The hand with fatigue muscles disabled is visibly less able to perform the target motion. We can also explore the redundancy in the hand architecture by randomly suppressing muscle groups that typically function together. Here we see the same motion being performed by 2 largely different muscle sets. Stressed and pulled muscles can also be simulated by disabling muscles that have contraction levels and lengths which exceed given thresholds in the best fit solution. We recorded a male and female subject performing various American Sign Language words by using optical motion capture.
ASL.
We use this data to validate and in the future calibrate our hand model by observing the errors in the inverse simulation.
LSQ.
The error is greatest for the wrist, since wrist stabilization is a challenging biomechanical problem. Helping hand can also be used to validate and improve the quality of synthesized hand animation. In this clip, algorithmically generated realistic hand postures were linearly interpolated without regard to hand dynamics. We first see that this motion is difficult to track using an inverse simulation. We then provide only the hand postures as targets over time to our inverse hand simulation and show that the resulting motion is not only less robotic but also richer than using keyframe interpolation. In general, anatomy-based inverse simulation shows promise in validating the realism of any given motion for a character of prescribed musculature.